Let us go back to the more classical field and then talk about retrieval of the aerosol extinction coefficients from the OMS LP limb measurements. I used the OMS LP limb measurements, but I think I don't need to talk about this picture anymore because Natalia has already explained it in detail. But I would like to say some words about motivation. Why do I want to do a new retrieval? And we had already have a retrieval of at the University of Bremen of the aerosol extinction, but there was found that there are some nasty features of the product. First, was a quite large positive bias in the extratropics. Then there are some quality issues below about 18 kilometers. No retrieval was possible below 20 kilometers. And they had a strong dependence on everywhere information. And so retrieval failed in the presence of highly elevated aerosol plumes, as we had in the case of Hunga-Donga eruption. And now it's just a brief a discussion of the differences in the different versions. This is the old one, labeled 109, and the new one has the name or version number 2.1. They both rely on the extinction at 869 nanometer. I will discuss it in more details in next few slides. Why? So the aerosol layer, it was at 1245 before, now it's 0 to 50, the same log normal distribution as before. Tangent height range was also extended from 1237 to 848. So before we had a normalization at a higher limb tangent height, and now really essential change is the normalization to the solar irradiance spectrum, which this causes difficulties with the surface albedo, which was just retrieved from the reference tangent height before, and now it's retrieved from the whole range of the tangent height simultaneously with the aerosol retrieval. So as I said before, it was just alternating retrieval, albedo aerosol. Now it's a joint retrieval. And before, it was sufficient to use the approximative spherical mode of Schiatran, which is quite fast. Now we unfortunately have to use the full spherical solution, which is really slow. And it's again the regularized inversion, nonlinear inversion, and inversion as before, but now it's also additionally constrained by the Levenberg-Marquardt approach. And it's the regularization is the same. It's a zero and first order Tikhonov terms. So now a couple of words why we're still staying at 869 nanometer wavelengths, and these are two plots. On the left, this normalization to the tangent heights, on the right to the normalization to the solar spectrum. And this grayish color, these are different wavelengths as they, for example, used by another retrieval. And I just analyze if we should switch. And what we see here at here 675, we have O2 absorption on the boundary of the spectral range. By the way, this is what is here marked as a spectral resolution of the OMS LP measurements. So this means this is the twice a half width of half maximum, which you see here. And the same feature we have for 760 or 65, 745 nanometer was it. Here we also have an ozone absorption band. At 869, this is almost nothing, with exception of this funny feature if you want to normalize to the upper tangent height. But at the moment, unfortunately, I cannot say what that is. And to the 1 micron channel, it might be used, but it might be more noisy. So this what you see here is based on schematic data, so it's not necessarily the case for ohms, but still a general case that the detectors get involved towards infrared and getting more noisy. And additional justification to use exactly these wavelengths for the retrieval, this is the sensitivity. So here I plot on the left averaging kernels for 3 wavelengths, 675 in red, 745 in green, and 865 in blue. And what do you see? So the blue and green are really similar, with a bit of differences here and there at at lower altitudes. But 675 has a really lower sensitivity if you go below 15 kilometers. So the sensitivity starts rapidly to degrade. And this was also the background of my question to Didier, because if the intensity, so if the sensitivity degrades, you have less sensitivity to the particle size, which is related to this this measurement. So the vertical distribution, same colors. Again, you see the best vertical resolution down to 8 kilometers you get from the 869. Similar but a bit worse for the from 745, and quite degrading below 12 kilometers for 675. And same situation actually for measurement response. So, and now most interesting feature we have from our new retrieval is the dependence on a priori information. So what we have here, these are three different cases, just single measurements, and the upper plots, they show the older version with different a prioris, different colors. The dashed lines shows a priori, the solid lines the results. And what you see in a classical retrieval, so in the old version, you have a really large difference. If you change the a priori by a factor of 2, the solution changes more or less by the same factor. And if you use the normalization by the solar radiance and tricks to fix the surface albedo retrieval, they are almost independent on the a priori information. So if you change the information by a factor of 2, you have just small differences at lower altitudes, but nothing in the essential range. Okay, and one more features. This is this artifact what we get with the old version. So if you have the plume high at the region of the reference tangent height, you have this nasty artifact with very low values below, just because you normalize to the completely wrong value. And then the new version doesn't have this artifact anymore and shows the plume even up to 38 kilometers in this case, and we are quite happy with this behavior. And now shortly to the validation of the new version. So this is comparison with SAGE 3 for the year 2018. Here the old version is in green, so sunrise and sunset measurements are shown separately with dashed sunrise and solid sunset. And what you see, so this large bias and extra tropics are now removed, and we are well below 25% for all the comparisons. So the same picture for all different years of SAGE, and what we see here that actually only 2025 here and there, it's a Hungatonga year, they have quite large differences, and all other differences are more or less the same for different years. And here, just a couple of examples. Again, this is Osiris in red, OMS LP green, and Sage in blue. So what we have generally a nice agreement between all the records in the background aerosol period here and there and here and here. But if you go to Hungatonga Peak, you see the different satellites show completely different behavior. So here is Osiris is the largest, OMS is a bit smaller, and Sage is very small. So it's still the issue we would like to look at. So, and now just an overview comparison with Osiris. Here is the average above all the years from 12 to 22, and below the same, but before Hungatonga year, just up to 21. And you see that this blob is caused by Hungatonga eruption, and the remaining features are almost 10-20%, with exception of with polar structure. On the left, you see the same dependencies, but as function of time and tropics. This is only feature is remarkable. Again, Hungatonga, there the instrument disagree, and some points they have up to 30% difference, but mostly it's 10 to 20%. And actually, a similar behavior for northern and southern mid-latitudes, with exception of some hotspots. You are really in a 10-20% region. And now I would like to show an example of Hungatonga year. This is comparison from the it's August 2021 to April 2023. And what we see here, so the dashed black line shows the Hungatonga eruption, the largest Hungatonga eruption. This was 15th of January 2022. And what we see, so we have a really immediate jump of the extinction after the eruption, and the perturbation is even with your eyes is seen up to 33 kilometers. And then the extinction starts to relax, so there is a clear sedimentation of aerosols, and this blob goes down, and here there is some region with a small extinction remaining, and this was the southern mid-latitudes, and the tropics. It's also the same, so they get the aerosols at 25 kilometers, and it starts to relax then, and here in then lower layers we still have some quasi unperturbed state. And these are two lat-long cross sections for 24 and 21 kilometers, and again, we see at 24 kilometers, this is the Hungatonga, the time and latitude of the eruption. And we see, so at 24 kilometers, you have more or less immediately the aerosol plume, and then it quite sharp shape it, and then it starts to relax. But at 21, it's initially small, and then it sedimentates, come down from the upper latitudes, and then starts to spread. And now I come to my conclusions. So we have developed a new algorithm to retrieve the extinction coefficients from OMS measurements. So we have extended vertical coverage, strongly reduced dependence on everywhere information. It's applicable to sense with high aerosol plume elevation. So we have generated and verified the whole data set with a good agreement with Sage and Osiris for background conditions, but some disagreements between all three satellites for strong volcanic eruptions. And for Hungatonga example, so we saw the perturbations up to 33 kilometers directly after the eruption, and strong increase in aerosol loading below 27 kilometers. Then the plume starts sinking after more or less 4 months after eruption. And the relaxation starts at the end of 22 and to beginning of 24. And for the time now, so the atmosphere is not completely relaxed. It's still highly elevated aerosol. That's all for me. Thank you for your attention.